Okay. Now that Dr. is here, we can start. No, the timing was just perfect. Yeah. Okay. So last class, we saw this this slightly strange model of catalytic computation, and we saw some surprising, at least surprising to me, ways of somehow using what seems like unusable space to do things beyond what just log space was able to do. Since there may be a few people who weren't there for the last lecture, catalytic space was the situation where you have a Turing machine that is working with a workspace of about log n, and it has additional space, which is perhaps polynomially large. But this additional space is going to be instantiated with something that you don't have control over. And the expectation is that when the Turing machine finishes the computation, whatever used to be on this catalytic tape is supposed to return to its original state. So the contents have to somehow return. And the question was, is there something here that you can do which is beyond just what you could do with the workspace? Like if you didn't have this catalytic tape at all, this is like a log space machine. But with this catalytic tape, can you do anything non-trivial? And in the last class, we sort of saw that this class CL somehow strangely not just contains NL, it even contains some larger classes which are called log CFL, which I didn't define. But at least for people who are familiar with NL, at least it at least contains NL. It seems to contain much more than NL. So that's one of the things that we saw. But although it's a good thing to have in the back of your mind with respect to how these computations work, today's lecture won't really need it, in the sense that there's no result of the previous lecture that we will be using, but the algorithm is inspired heavily by catalytic computation. So, okay. And so in fact, today's lecture is going to be on this thing called the tree evaluation problem, which I will soon describe. But let me maybe give you a little bit of history for the tree evaluation problem. And it all starts off with this belief that we seem to have that log space is a strict subset of P. Okay, and we would really like to show that this is a strict subset. So if you wanted to show that this is a strict subset or something, what you would like is a natural problem, which you know is doable in P, which perhaps is not doable in log space. Of course, you could take a problem that is P complete in the sense that and show that that is not in log space. But sometimes it might be convenient to take something that seems to have a slightly different flavor, because maybe the standard complete problem is something that is almost synonymous to P, and we may not be making progress. And in 2012, Cook, McKenzie, Ware, Braverman, and Santanam, they introduced this problem called the tree evaluation problem, which is what this entire lecture is going to be about. So let me define what this problem is. And it usually has two parameters. There's a parameter called H, which sort of refers to the height of the tree. And there's another parameter which is called K, which is something about, I don't know, the alphabet involved. Okay, I will soon describe. So the mental picture you should have is that you have a height H tree where every node is like a function. There is a function, and I'm calling the nodes by just, let's call this the empty set. This is the node 1, 0, this is the node 1. And this is the node 0, 0, this is the node 0, 1, etc. You just give some names for these things. And let's imagine at every node, you're given one function. Okay. And at the leaf levels, you're going to be given some k-bit string. Every leaf here is going to be given a k-bit string. So formally speaking, for every nodes that are like 0, 1 to the H refers to things that are at whatever, at the bottommost level of the tree. So there, let's say someone gave you a k-bit string for every such node. And for each binary tree. Yeah, this is a binary tree. Today I will focus completely on binary trees, but you can imagine this problem in a more general setting as well. Okay. And for every internal node of this tree, imagine a function that takes two k-bit strings and returns a k-bit string. Okay.
Function is also part of
yeah. The input is going to be specified by, I will tell you what each of these VUs are, and I will tell you what each of these functions are. So that's going to be I'll soon specify precisely what the input is. Okay. And in addition to this, basically what we want to do now is, suppose I gave you all of these functions somehow. Let's say explicitly I told you what these functions are, and I gave you the values at all the leaves. you can imagine just propagating this all the way to the root. Basically, if you know the value, what was I doing? So that is, if you know the value here and here, you now sort of know the value there because the function tells you what you need to do, given the two children. Okay, and you keep doing this, start from the leaves, go all the way to the top. And I want you to tell me what is the value that you have at the root. I mean, and if you're going to put me on a spot and say that, no, this has to be a decision problem. Okay, I tell you that, can you tell me what the first bit of the output is or something? But I mean, like, this is something that we can always move between. So we'll just say that the computational task is I give you this input entirely, and I want you to tell me what the value of the output is. Okay, so let's get a sense of what is the input side. What do I mean by I give you this as inputs? So let's say every function, I write this function down explicitly. I basically say if the inputs were x and y, this is the function value. Since I'm giving the truth table. Okay, that's what is provided to you for every internal node. And at the leaves anyway, you have a k-bit string. So what is the total input size going to be? So there are 2 per h leaves. Each of them is going to be given a k-bit string. This is just the leaves ka input itself is like this much. Plus, for every internal node in my tree, I need to now give you this truth table. That is, for every pair a comma b, where a and b are both k-bit strings, I need to tell you what is the function value going to be. Okay, so that is roughly going to be what, 2 power 2k times, I don't know, k or something like that. Like for every pair, I need to tell you what is the k-bit string that you output for that particular pair. So this is the overall input. I'm just going to say this is basically like 2 to the something like order of k plus h. That's the input size. Okay. And since we are just familiar with dealing with polynomial in the input size or something, if you want to set this to be equal to n, the right parameter regime that you should have in mind is that both h and k, think of them as being order log n. That's the parameter regime to have in mind, but you can imagine that h and k are just like free floating parameters, and you might want to do something based on. So is the tree evaluation problem clear? So you are given the leaf values, all like 2 per h times k-bit. You're given k-bit strings for every 2 per h each leaf, which are 2 per h leaves. And for every internal node, I give you the function entirely. I give you the truth table completely. And I ask you, what does this tree evaluate to? So that's what is called the tree evaluation. All right. Now, the first observation is that this tree evaluation problem is clearly in P. Again, whenever I'll always be working with h and k as being order log n. Okay, so it's clearly in polynomial time, which is you do the most obvious thing. Start from the leaves, just keep evaluating all the way to the top. Like nothing here is fancy. Okay, so now this is why we are going to say that no, this is perhaps a good candidate for separating P and L. So let's ask ourselves, if you tell me that I want you to build a low space algorithm for it, okay, what can you possibly do? Okay, and let's try to write down what is a naive, like space efficient algorithm you could write down. And the first thing perhaps that comes to mind is let's say you first compute the tree evaluation of the left subtree. So this is going to be a tree evaluation problem of height h minus 1, maybe on the same alphabet size on whatever left subtree. I mean, you know what that means. I mean, just take the corresponding things there. And then you look at alpha r, which is going to be the TP h minus 1k of the right subtree. And you basically return whatever was the function at the root of alpha L and alpha r. Okay, and obviously, when we are doing this computation, we might have used up some space. So after we finish the computation, we erase off all of that and then try to repeat. Okay, and now let's get a sense of how much space does this algorithm end up using. Okay, I tend to think of these as it's like a stack, like your memory stack that you have in your program. So basically, let's say you run this first computation somehow. You found the value of alpha L. So you would have probably stored the value of alpha L in some particular variable or something. And now you're going to run the recursive call on the right subtree. So the right subtree will again use some more stuff. So intuitively, hopefully you see that this is basically the space that you need for h minus 1 times k plus this local memory that you have before you run these recursive calls, which in this case is like order k bits. That's how much alpha L seems to take already. Okay, and so if you work this out, you're going to end up with something like order hk. And it sort of seems to make sense because if you're going to compute this tree, at some point I might have to store the left child's value and then do the recursive call. But that recursive call will say, hey, temporarily store its left child ka value and do the recursive call. So it somehow looks like you need to store the values of h different, intermediate computations. And each value seems to take k bits. So hk seems like what you would get in this thing. Okay, and in fact, this was formalized by something called a pebbling argument. If people know that if you want to do pebbling, then this is basically the only thing you can do. Okay, good. So that's going to be the thing. And just to keep in mind, this for our regime of parameters, this is like log squared n because each of h and k were like log n individually. Okay, and so for a long time, the conjecture, at least in the initial paper of Braverman et al., etc., it was conjectured that perhaps log square n is tight. And they actually showed that the conjecture seems to hold if your algorithm is of a specific nature. Like if you're doing a sort of pebbling kind of idea or something, then maybe log square is tight. But it was a conjecture to say that can one show that this requires log square n space? To the extent that apparently there was a prize money that Steve Cook had, that if someone can prove or disprove this conjecture, I don't know what the amount was, $100 or something like that. $100. Okay, yeah. And in 2021, Cook and Mertz showed that no, log square n is not the right answer. This is no. This is yeah. Okay, so they basically showed that you can shave off a little bit. So it's like log square n over log n or something. Okay, and now would you say that deserves the the whatever $100? Did you really mean log squared n, or no? Now maybe you change goalposts and say that no. I truly meant log power 2 minus epsilon. You can't do or something. And then in 2024, they basically said that it's almost log n space. Okay, in fact, the space complexity of the tree evaluation problem is log n times log n. So it's like almost at L. Like if the log n factor were not there, this would have been basically said that TEP is an L. But this log n factor is the only thing that is pushing it away from L at the moment. Okay, so this is going to be the main theorem that we are going to prove today. In fact, in general, if you have a TEP situation where you have two parameters h and k, then the space complexity will turn out to be h plus k times log k. Okay, and if you instantiate both h and k as log n, then you get log n log log. Okay, so is the question clear what we are going to try and do? Great. So the algorithm is surprisingly short, and in fact, what I'm going to be doing is a description of Oded Goldreich. It was like a manuscript that showed up on ECCC maybe few months after the Cook Mertz paper, which is a far simpler description of what Cook Mertz do. So that's what I'm going to follow. But it builds on some, I need to have some preliminaries for it to tell you exactly how it works. But let me sort of briefly tell you what the idea is. Like, what is the idea behind this Cook Mertz algorithm? And the key is to do the algo catalytically. In fact, do the naive algorithm catalytically. Okay. So what I mean by that is the following. So let me just recall what the previous algorithm was. This is what we were doing, right? Like we basically said alpha L is the left child ka value, alpha R is the right child ka value. We compute both of them recursively and then compute the function value. So we're going to basically say, in some sense, let's think of the point where we have computed alpha L so far. So k bits of memory is currently holding the current value of alpha L. Now this algorithm, this recursive call needs to run. Now this recursive call might say that, hey, I need a certain amount of space. The previous algorithm was giving it fresh space, saying that, look, the alpha L is currently being stored by the stack. I need to use that value separately. So I'll give you fresh space from now on. You start working on it. Instead, what's going to happen is we will instead tell this recursive call, you can make use of this alpha L register that was there. There is k bits of space in it. But the expectation is that when you finish your recursive call, you better put back whatever was in that register. Okay? And so which basically we are going to expect more from what the recursive call is going to do. But hopefully you can sort of see that we are doing some space savings here already. In a very, very high level, that's basically what's going to happen. We are going to, there's going to be some global memory, which we will give complete disregard to. Every recursive call will go and mess up that global memory. But we will try to do it in a way that is very structured. Okay, so that at the end of the call, it somehow looks like a catalytic computation where, we'll see what happens here. Okay, so that's the broad overview of how the TEP algorithm is going to work. And it will basically turn out that you will only need to have essentially the space that you require for the left child multiplied by one log n factor. That's what it will turn out to be. Rather than using fresh space for each of the H recursive or whatever, the depth H recursion, we will basically reuse this global space a lot. Okay, so this is the overall picture of what the algorithm is going to do. So I'm going to take a slight detour into stating some sort of perhaps common algebraic facts, like things that you probably encounter in other contexts also. And we will see how that fits in. So since we are dealing with catalytic space, stuff like that, we will have to deal with polynomials and some properties of these polynomials involved. So I want to start off by telling you a little bit about this thing called polynomials and extension. Okay, so the setup is going to be that we have a function f which takes a k-bit string and takes two k-bit strings and returns a k-bit string. Now, okay, this is a completely unstructured function. I have no control over what this function is. But it's sometimes nicer if this function has there's a nice polynomial that corresponds to this function or something. So what we will do is, let's imagine that we just choose our favorite field, which is this, let's say the field on 49 elements or something. So choose your favorite field. The nice thing about any such field is that it already contains a symbol called 0 and a symbol called 1. Okay, so what I want to do is, this is the bad picture for f cross f. Think of the rows and columns as being indexed by f. But, let me call it bad picture of, let's say, f to the k cross f to the k. So the rows are all indexed by like k length vectors over the field. Columns are indexed by k length vectors over the field. But there is a small subset of vectors which correspond to thing of the form 0, 1 to the k cross 0, 1 to the k. Right? It's just that I want to think of the function domain was just 0, 1 to the k cross 0, 1 to the k. But I'm pretending that this was actually in a larger world. And the function is just telling you what value you should be taking here. That is, it is telling you which of those values must be 0 and which of those values must be 1. Now, what I would like to do in any such, when we are talking about extensions, is that come up with a different function, which let's say I call, okay, right now the output itself is a k-bit string. Let's imagine focusing on one of those outputs. So the output is either 0 or 1. Okay, but I want to think of that as hopefully a polynomial, which takes k variables and k variables for the x's and k variables for the y's, with the property that whenever I feed in values which are zeros and ones, I want it to agree with whatever function it was. Okay, but if I feed it this value or something, at the moment I have no expectation of what that is going to be. My thing is, I know the given function takes a specific behavior on this small region, and I want to extend this behavior to the larger domain. Okay. So this is what I mean by, we will say this capital Fi is an extension of small fi. If it turns out that whenever you feed in 0, 1 values, it behaves like the old function was behaving. Okay. And we would like an extension that has as small degree as possible. I would like a nice extension which somehow captures this behavior that I want. Okay. And I guess people have sort of seen this before. Like in some sense, this is like saying that someone told you that, I want something that takes value alpha 1 at this point, alpha 2 at this point, and alpha 3 at this point. I just gave you 3 points. But now I'm going to tell you, no, I want this to be a parabola. Then what you would have done is you would have done some interpolation to figure out, okay, let's find the parabola that has these values, which now allows me to evaluate this parabola at, I don't know, pi or root 2 or whatever. You're going to do something very similar. Okay. And the most standard thing to do is, this is like the Lagrange version of it, which is just imagine that you have some polynomial which is called delta, whose role is the following. It takes x comma y, and if the x comma y happens to be a 0, 1 bit string, if that was equal to a comma b, it will return 1. Otherwise, it will return 0. So it's like a delta function as far as the small domain is concerned. And all you're doing is you're basically using this to say that, at a comma b, I want you to take value f of a comma b. And you set it up this way. And building this delta is also like completely trivial. Okay, this is one example of delta that works. Okay, like each term looks like, if xi is equal to ai, you return 1. If xi is different from ai, you return 0. And I've just taken a product of such things. Okay, it doesn't matter what this thing is. You can build your own examples of some variants of this, but this is one variant I like because the degree of this polynomial now turns out to be at most 2. Okay, because each of these terms, like each of the terms that are here, this is a degree 1 term, this is a degree 1 term, and I'm taking a product of k such things. So the degree is at most 2k. So what is this basically saying? Let's zooming out. We had an arbitrary function which had no control over what this function looked like on some small domain. And what we are saying is, I'm giving you something which is called an extension of this function, which has degree at most 2k. That now gives you a way of assigning values over this entire domain. Okay, so this is what is called, it's called a multilinear extension. There are many names for this. Okay, so good. So now, okay, this was just some random thing about it. But first thing is, I want to basically say that computing these extensions are fairly easy when it comes to space. Okay, specifically, if I give you a specific function, this thing, and what I ask you is, can you tell me what this multilinear extension is going to compute at a certain point? You can do this easily in roughly order k space. I mean, if the field was small enough, it takes about order k space. And the thing is just some monomial by monomial. I shouldn't say monomial, let's say term by term. What I mean by that is the following. What is this capital Fi at this whatever, this alpha comma beta? This is going to be, there is this big sum over all the a's and b's on 0, 1 to the k. And something that looked like f of a comma b times delta a comma b at alpha comma beta. And delta itself was a product of some k such things or something. So you could literally do things one by one. You just store a comma b in your memory, have a running sum or something, compute one monomial, add it to your running sum, move to the next a comma b, keep repeating this again and again. And you can basically see that the space that you're using is essentially to store these intermediate values, current values of a comma b's, etc., plus whatever extra space you might need for doing some field arithmetic. Okay, so and all of this is therefore doable in about log n space. All good so far?
Sorry, the image of this is.
Oh, sorry. I should have basically, I mean, if you have a multi-output function, just imagine doing it at every coordinate. So whatever the superscript I refers to, you're only going to look at the ith bit of the function, the ith output bit of the function. So in some sense, It's like as if I'm thinking of this output k tuple as a k tuple of polynomials, one for each of the coordinates.
So, every intermediate state, what you're maintaining is the field element.
So basically here what I'm saying is that if you tell me which fi you want to compute, I just need to maintain at an intermediate state just the field element, plus along with, I don't know, till what level of the summation have I done so far. So I might have to keep track of my current value of A and B in this like summation that's sitting on the outside. Sorry? Yeah, the whatever you need to do some field arithmetic. So it comes from that. So just imagine, basically think that, if you can do your field arithmetic within order k space, then that log f is just not important. Why is it k times log f? Yeah, it's like, yeah. So. Okay, good. Okay, so to make life simple, I'm going to do the following. The standard tree evaluation question, what was given to you by these functions along with the leaf values? Okay, I would like to work with these extensions. Like rather than given the functions being given to me, suppose I were given these multilinear extensions over some field, and I promised you that we will be working with the size of f. This will be about 2k, something like 2k plus 1 or something. That's what we'll eventually end up working with. So the fields are not very large. Okay, so let me give this thing a name. This is the standard TEP. This I'm going to call, I don't know, TEP star over some field f.
So by 2k, you mean some parameter 2k also?
Yeah. So I just want the field size to be larger than 2k. Right now, why I need that is unclear, but it will soon show up there. Okay, and I want to basically say, if you tell me that I can do this problem efficiently, like if I can solve the TEP star problem efficiently, I want to claim I can actually now solve the TEP problem also efficiently. This is the standard thing of what we do in log space reductions. So notice that we just showed going from this to this other world required something like order log k space. Right? We basically said that if you gave me the original representation, I'm telling you how to build the new representation. So it's like as if you did a log space reduction and then you're solving this new problem. And we have seen in log space completeness, etc., that if you wanted to do this, you will basically just take this plus whatever space you need for the reduction, plus maybe log of, let me just write it as L, where L is the length of this overall. Because when you recall what is happening in a log space reduction, you might have to keep track of which bit do you care about. And then you will just run the log space reduction until that point to figure out that bit. But basically what we are now going to do is like we'll now start focusing on the TEP star problem. Prahlad, you have a question? Oh, sorry, not log k. I meant, yeah, this is like order k space. Because that's how much time our reduction is going to take. So this is also order k. Order k is like order log n. Okay. L is the length of the. When you do this log space transducer, there is a length of the output that you have now. If your original input had length n, this new whatever multilinear extensions have length larger. So it will be log of that thing. Basically the point is if you have a log space reduction from one language to another language, and if you know how to solve the second language, the extra space you need to solve the first language is basically whatever you need to run the reduction, plus whatever you need to index into one bit of the output. Okay, and both of this are
log space reduction from this length of the output date.
Yeah. So that's the only reason we need. Okay, but basically this means I just want to focus on the TEP star problem and just say that no, we are given these functions as these low degree polynomials, and we'll work with them. Okay. One more algebra fact, which is this thing called interpolation. In some sense we've already used it, but we're going to use it once more. And the moral of interpolation is that if you have a polynomial of degree, let's say strictly smaller than d, which basically means to know the polynomial, you need to know its D coefficients. So interpolation tells you that rather than giving you these coefficients, suppose someone had told you what value this polynomial takes on D different points. That's basically enough for you to know the polynomial entirely. Okay, like it's like I can tell you a parabola by giving you the quadratic by those 3 terms, or I could just tell you the quadratic takes this value at 0, this value at 1, and this value at 2. That's sufficient for you to know the polynomial entirely. Okay, and I hope people have seen this before. So it just follows from the fact that there's a standard nice transformation of going from the coefficient representation to the evaluation representation, which is just multiplying by an appropriate matrix. So if you have a vector of coefficients, how do you get the vector of evaluations? Well, we multiply by the corresponding Vandermonde matrix or something. And the nice thing about this Vandermonde matrix is that it's a D cross D invertible matrix. And therefore, I mean, if what I had was the evaluation representation, getting the coefficient representation is like multiplying by this V inverse. Okay, so something that we'll specifically use is that if what you care about is the value of a polynomial at 0, but suppose I just told you the value of this polynomial at many other points, things other than 0. This basically says you give me D other points, that's enough. I can tell you how to, take a linear combination of those to figure out the value at 0. I mean, in this particular case, value of the G of 0 is just the first term here. That's basically this row inner product with this guy. So if the rows correspond to gamma 1 through gamma D or something, then that's what this turns out to be. This is just standard interpolation that hopefully people have seen before. Okay, since we are doing low space computation, I need to basically say that, like there's also this thing of how hard is it to compute these gammas or something. I will just state this and push it under the rug. Basically, if you choose your alphas to be some nice expressions, turns out the gammas are also nice. Like for example, usually what is done is you take alphas to be roots of unities or something. Then the gammas will also turn out to be some roots of unities. So these are all computable easily. Okay, but I'm not going to, I will just, I mean, this has to be true, if not for this alpha or some other choice of alpha. But throughout, when we are doing our algorithm, we might encounter some situation where we have to figure out what this gamma is. And I'll just assume that all of those can be done efficiently. Okay, so let me just do a recap of the 2 preliminaries that we needed. The first one was going from the standard, Boolean representation of some function to somehow expanding this domain a little bit. So you're going to work with a field not of size 2, but of size something like 2k. That's what we'll be working with. And we just want to extend this function f to the entire world. And fortunately, there is a fairly easy way of doing that, which is space efficient way of doing that. So we're going to work with a tree evaluation problem where these are the functions that are given to us. Okay. And the first thing we noticed was that going from the old problem, this TEP to the TEP star, doesn't really cost much in space. And the next thing, which is at the moment unclear why we need this, is the fact that if you have a univariate polynomial of degree at most D, and if someone told you the value of this polynomial at D different points, from this you can recover everything about the polynomial.
D plus 1 divide.
Okay, this is okay. Yeah, one less. I was careful while writing it in the sense that this is a polynomial of degree at most D minus 1, so it has D coefficients and stuff. Yeah. Okay, and at some point, because our polynomials had degree 2k, that's why I will need 2k plus 1 evaluation points, or maybe 2k plus 2 or something. We will see what happens in the proof. Okay, good. So now I'm going to basically describe what the Cook Mertz algorithm is. And we will do 2 attempts. We'll almost get there, and then we'll put them together to actually get the final answer.
We are directly doing Cook Mertz 2, not the.
What is Cook Mertz 2?
Not the log square and by log.
Yeah, I am doing log n, log n. Yeah.
What do you do in log square? Okay,
That's a good point. I haven't read that paper. I don't know. Yeah. Okay. So what is the setup? The input that is given to us, now I'm going to assume is that this is the truth table that's given. Now the truth table is over f to the k, not just I mean, it's a, okay, all that is like sort of written down. I mean, it's already a little larger than it used to be. I mean, previously it was polynomially large, but now it's like k to the k sort of large. Okay.
Find that. So the only is a k bit output.
Oh, right. If I putting a k bit thing, then there is no I. Or let me do it this way. So for each of the coordinates, I give you one column. And along with that, you've also given the leaves. I'm still assuming the leaves are 0, 1 to the k because I mean you can interpret it as some arbitrary element of f to the k if you want. Okay, and the promise is that all of these fi's have degree at most 2k, and we're going to be working with a field of size. Basically, I just wanted to be a little larger than 2k. I mean, 3k is good enough. Like Srijata was saying, just pick a prime between 2k. I mean, 2k plus 5 and 3k or something, that should be good enough for us. Okay. So what is the memory model going to be? So I'm going to be, so that, we have, this is the way we are going to work with. I'm going to tell you the program is going to have some global memory. And recursive calls will mess this up. Okay, it will go and mess up this part of the global memory. But it will also have some local memory that it is. And the global memory will basically be, so there will be a register which is of, length at most h, which is storing the name of the current value probably. The current whatever node ka name. So each node is given a name. The root has a name, which is the empty set or the empty string. Then it is 0 and 1, then 0, 0. And so the value of the name of the node will be stored in one register, which, this is not the really catalytic part of it. But then we are going to have 3 other registers. Let me just call them tau1. They're initialized to values tau1, tau2, and tau3. I will call the registers as R1, R2, and R3. And each of them, in some sense, will be holding values in f to the k. So that's what these registers will hold. Okay, you can think of them as maybe made up of k blocks, each of those blocks as having one field element. Is this okay so far? Good. And let's pick some notation. Let's call VU for when U is of maximal length, that is, it's of length h or something. That's the leaf value. Otherwise, V at any intermediate thing is you just compute the corresponding function. That's the value of this particular thing. Okay, this is just some notations.
So the field size choice is the total degree of the.
Yeah, so it will turn out once we see the algorithm, we'll see that I will need the field to be at least as large as the degree of these f's. And that's the reason why I'm working with a field size just above 2k or something. Okay. So what we would like to do is the following. I would like to build a program PU. Technically, the U is going to be stored in the first register. It tells you which function you are applying. But here's what I would like to do. I want a program that basically has the following behavior. If the registers R1, R2, and R3, they're instantiated with tau1, tau2, and tau3. After I run this program, I want the registers to hold the value of tau1, tau2, and tau3 plus V.
What is VU?
VU is the value that you would have taken at that particular node. Like if you start with the leaves and you go all the way to the top.
So where do you have VU0 and VU1? Where is that?
So the thing, so basically for all the U's that have length h, those correspond to leaves. So they were given to you in your input. Compute all subsequent things using the function. So the value at the node U.
No. So at an intermediate step, where is VU0 and?
Like for example, if this is some node U, there would have been this is the node U0 and this is the node U1.
Yeah.
So let's say you did the tree evaluation and got a value for that node. So that was VU0. You did the tree evaluation here, got the value for this node, that was VU1. Apply the function FU on those two things. That is the value at VU.
I think inductively you just say I have the ability to compute the value at U0. I have the ability to compute the value at U1. Now show me how you will compute the value at U.
Yeah, so we are going to build programs from the bottom up. So if it was a leaf and I asked you to come up with a program that has this behavior, That is easy to do because the value VU was actually written on the input table. I just copy that value, I just translate that particular register by that value. So that is trivial to do.
You need some extra space to add. Store the derivatives.
Store what bits?
If you're adding VU to the other thing.
Yeah, but I just need enough space to do field arithmetic.
Oh, that's some extra.
Yeah, but all that will be chiller basically. Okay, so this is what you would do. But the point is, it's unclear how you are going to do it at some internal.
Induction hypothesis, if U is given in the zeroth register, then you can affect this.
Yes, technically speaking, I should be saying that if U was put in the zeroth register, there is this one program P, when instantiated with these 4 registers, results in this. And right now, I know that the program can achieve this if U was basically a length H label. If it's a leaf label, then I know what to do here.
From log f extra.
There's some extra space that I might need, but
log k extra thing.
Okay. So, but we want to do this somehow inductively. I need to tell you how to do this in a larger situation. Okay. So inductively, like Jayakumar was saying, let's assume that we have programs PU0 and PU1. Okay. That achieve computing the value of VU0 in register 1. And similarly, computing the value of VU1 at register 2. It doesn't matter which register you're going to compute it in. You can always repermute them as needed and stuff. Somehow, using these 2 programs, my job is to come up with a behavior that looks like this. That's what I have to do. And I don't want to use too much extra space in order to do this particular. Okay, good. So here is attempt 1. We could try the following. Let's run program PU0 first. Then let's run the program PU1 after that. And then let's just do the following. Okay, R3 register has some I blocks, some K blocks in it. So for each block, we will replace that block with the function value computed in those 2 registers together. And we will increment it by that particular value. Okay. And then because I want things to be I want the other registers to return to its original values, I will run the inverse of PU0 and PU1. This way. Okay. So note that, if the register values were initially 0, then this is a perfect computation. Because it would have been 0, but after I run PU0 and PU1, I would have gotten the right values in those 2 registers. And that gets added to the 3rd register. It's exactly what I want to do.
PU0 puts its output in register 1.
In register 1. I'm assuming PU0 puts it in register 1 and PU1 puts it in register 2.
If tau1 and tau2
If tau1 and tau2 were 0, then this program would have done what we wanted it to do.
What does PU0 inverse now?
I'm assuming that all the programs are going to be made up of instructions of this type, similar to how we were doing in the catalytic computation, etc. Every such instruction will obviously have an inverse instruction. So basically this instruction is just going to be replace R3 with R3 minus this quantity. So you can take the instructions for PU0, like step by step you do the
Tau1 drops by VU.
Yes, it will reduce by the VU0.
Okay.
Tau2, when you run PU1, what am I doing? When you run this particular program, the register will reduce by the value of VU1.
You can run the characteristic of it.
No, I don't want to do. I want to do it. Then no, but the program length becomes size of F many things, right? In the sense that we'll be doing more complicated things that I want to take inverse of. It won't just be pluses of this type. So, okay, so this is one way in which we can try to achieve this. But the problem is what we do is register 3 ends up with this value. And whereas what we want is to end up with this value. In the previous thing also, right? Because the registers didn't start off with some 0 values. It started off with values that are not in your control. So which means when I apply the function fu, it will apply the function fu after not taking into account whatever those registers held. and therefore you will end up with not quite what you want. Okay, so this is not quite doing what we want. Okay, now let's try another attempt. We are just going to try and come up with other ways of doing it and then see how we can put them together. Okay, so now what I'm going to do is I'm going to imagine, let's imagine register 1 and 2 held some values. You pick your favorite non-zero field constant. Let's say it is alpha. Let's first scale both of these registers by that value alpha. Now this is also an invertible operation because I took a non-zero field constant. If I multiply by, just replace Ri with alpha times Rn. I do that for R1, I do that for R. Like imagine doing it for every coordinate because it had k blocks of field elements. Do it for each of them. Okay, this is an invertible operation. I can do this. And now let's run the old program as usual. I'm going to run P1 and P2 like earlier. Then run this update step. And then undo the programs P1 and P2 now. And unscale the registers 1 and registers 2. Okay, now let's get a sense of what will this now compute. Okay, it's clear that register 1 and 2 have returned to whatever their old values were. Because whatever, if it was originally tau1, it then went to alpha tau1, then it went to alpha tau1 plus VU0. And then it got the VU0 part got subtracted, and then the alpha part went up. So you went back to tau. Same thing happens to tau. But what whatever R3 holds is going to be tau3 plus FU of alpha tau1 plus VU0, alpha tau2 plus VU1. Because basically what we did was we ran the same program, but after we scaled the registers by a factor of alpha. So it just basically what was here, except you replace tau1 and tau2 with alpha tau1 and alpha tau2 instead. Is this okay so far? Great. This again is not what we want. So what would we like to have? I would like to set alpha equal to 0. Okay, but that's the scaling I'm not allowed to do because I have to do things in an invertible fashion. So I want to basically do some jugaad to figure out, I essentially want to get alpha equal to 0 there. But can I achieve that by doing these other scalings? Okay, and now hopefully you can see that this is just interpolation. Whatever you're doing is some polynomial computation which depends on this alpha. I would like to figure out the value of alpha set to 0. So we're instead going to try out many other alphas and take the appropriate linear combination to get what the value of alpha equal to 0. Okay, so let's just run this thing. So I'm going to define g of t to be equal to fu of t times tau1 plus vu0, t times tau2 plus vu1. I mean, maybe the ith coordinate or whatever it is. Doesn't matter. The thing is, like I don't really know what VU0, VU1 is because this is what the program, the PU0 and PU1 will put on those registers. Again, I don't know the value of tau1 and tau2, but the t is in my control. So whatever t I choose, the increment that is going to happen in register 3 is going to be this value. Okay. What I would like is the value of g of 0. Okay, but we just saw interpolation. And interpolation, this is some univariate polynomial of degree at most 2k in this indeterminate t. Everything else is some fixed constants that I don't have control over. Okay, so this is degree is at most 2k. So therefore, interpolation tells me that I can write this as I going from 0 to, I don't know, something like 2k of some gamma I times g of alpha I. Like if I choose alpha 0 to alpha 2k as distinct field elements, okay, which are not 0, which is why I need my field to have size at least 2k plus 2. Because there is a 0, I need 2k plus 1 other non-zero elements in my field. If that is there, then I can basically, from this particular linear combination, I mean, this is basically going to become equal to G of 0. Oh, sorry, that's what I wrote on the left. I don't know why I'm writing it. Okay, so let's just expand this this thing. This is basically going to be, this is gamma I times fu of alpha I tau 1 plus bu 0, alpha I tau 2 plus bu 1. And now this alpha I is in your control, the gamma is in your control. Now we're going to basically use this to rewrite our program that essentially achieves this. Okay, is this okay so far? So, oh, don't know what I left this space for something. I don't know what I've left this space for. Okay.
Combine gamma in the fu and call it a new function.
I mean, to me, fu is what is written on the input tape right now. I don't want to mess around with that.
What you add to tau 3 is f.
Yeah. So what we will instead, okay. So basically what I'm going to, all I wanted to say here was that, no, this is just interpolation. And we can basically build a program now. And what is this program going to be? This is what the program is. So I'm going to take 2k plus 1 different values. That's what this outer for loop is going to be. Okay. And what are you going to do in a for loop corresponding to I? So you scale the first register with this alpha j, depending on your loop index. Scale the second register also with alpha j, depending on this loop index. So for this, you first need to compute what alpha j is. Hopefully that doesn't take much time. I mean, much space. Okay. Now what you do is you run the programs pu0 and pu1 after that. Okay. And now, like Jaikumar said, previously we were just adding fu applied to those two register values. You just do the same thing with the scaling by this gamma j. Okay. And now undo everything that you did for registers 1 and 2.
What do you mean by scaling by gamma j? The whole program will be told, and every step, because this particular addition is being performed by an operation, right?
Oh, yeah. So let's imagine that, I mean, basically imagine the program that was, how do I?
Gamma j has to be something.
Maybe add something to the register.
Every instruction has to be.
Yeah, maybe okay. So I will
divide R3 by gamma j, then add fu to multiply by gamma j.
Yeah, you could do whatever. You like what Malhar was saying is like you divide R3 by gamma j.
It's not linear, right? Not j.
No. I mean, if for example, if gamma j's were non-zero, you could do what Malhar is suggesting, which is first divide R3 by gamma j.
Both R1
No, R3 by gamma j.
R3 by gamma
j. Run whatever this instruction,
Yeah, got it.
and then scale it again by gamma j. So that's one way of it.
If gamma j was 0, then you just skip this entire.
Yeah. So you could do something like that as well. There are many ways of. Yeah. So if you take alphas to be roots of unities, this is gammas will also be roots of unities. Nothing is 0 here, and all is okay.
Yeah, you do have an extra log f space. Log f and log k space.
Yeah. So basically, my local memory looks. I mean, I need to keep track of what is my current I index, j index or something, because that's what is going to tell me what is the alpha I and the gamma, whatever, alpha j, gamma j that I need to be scaling with. So I need to somehow store my current j. I mean, so that's what I was written. Okay, then I'll just come to that. But we'll see that, there is very little extra space that we need to use at this point. So what does Rj hold? Rj is going to now hold tau 3 plus exactly this thing. Alpha j tau 1 plus bu0, comma, alpha j tau 2 plus bu1, which we just observed that this is essentially, this is going to be, fu of, no, there's no tau. So this is going to be what? bu0, comma, bu, which is precisely what we wanted.
Now 3 plus 1.
That's summation gamma j.
Oh, sorry, this is gamma j going from, I don't know, 1 to 2k plus 1. Yeah, whatever. So I don't know what I think here, yeah, I probably switched between the zero index thing and whatever one it is. Okay, and this is the program. That's it. This is basically the Cook and Mertz thing. We're just now going to analyze how much space does this use. Okay, so the local space is just storing what is the current I index. I index is basically which function are you computing, like what is the coordinate you are changing right now. Okay, and I need to store, what is my for loop index, like what is the j that I'm working with, so that I know what alpha I need to multiply with and what gamma I need to multiply with, etc. Everything else is sort of ephemeral space for doing field operations. It's not like this, that space is going to remain when I eventually run these recursive calls or something. I might need some space to do that field operation. After I've done the field operation, that's gone. Okay, and the value is stored only on this global memory. I'm not storing anything locally. It's written on the top of this global register. So the local memory is just to store how much space you need for storing I and storing j. Okay, and therefore this is basically like order log k, because
Order k.
no, I just need to store the current value of j, and it's only one of like 2k different values. So I just need to store log k bits for storing j and log k bits for storing I.
Log f also for
Log f is not something that need to stay on the stack when I'm doing the recursion. Log f is what I need to do arithmetic, but after I've done the arithmetic, it's not space that remains on the stack. I mean, I need to be, I don't want to keep adding, I don't want every recursive call to add a log f to the. Yeah, if you want, you say, if you're doing field operations, here is log f memory, you use that for your field operation or something. Okay. So this is what your local storage is going to be. And so therefore the local storage for running the program PU, because PU required running the program PU0 and PU1. Okay, that's basically going to be whatever local space you need for the sub-programs. In addition to that, I might have to store my current I value and current j value. Okay, which is like log k bits. And therefore, the overall space is essentially going to be something that looks like this. The global space looked like the space to store the name of the whatever node you're working with. That was h bits. And then there was this 3k register, which all involved field elements. And a field element is like roughly log k bits again. So there's going to be h plus k log k is the global register cover things. Plus, since the recursion depth is like h or something, and the local storage I'm using is like log k, I will have this additional h log k that adds up.
How do you get h plus k log k?
So h plus k log k is the global register thing. So my global register is going to be storing this u value. I mean, I need to know what is the node I'm operating on. So that is h bits. Plus the space required to store these three registers. These three registers look like 3k different cells, each of which is holding a field element. So that's a k log k from that.
Did you give the h log k one?
So h log k is because when you do the recursion,
Okay, fair enough.
okay, so that's what is going to give us the extra h log k. So this basically amounts to something like h plus k log k. And again, for our choice of parameters, recall that both h and k were like log n or something. So this is going to result in log n log. Okay, it's a very simple. I mean, like it's a really smart, really clever this thing, but on the face of, I mean, it's a fairly simple argument.
Just one minor thing. So,
Yeah.
you wanted our function to put the value on the third register.
Haha.
So you assume that these two things put it on the first and the second.
Yeah.
You need to keep tab of where.
Okay, let's
how
add one more bit on the top to basically tell you whether am I supposed to store it on register 1 or 2 or 3.
Which of the 6 permutations of 1, 2, 3 you want?
Yeah, you will store that also if you want. Yeah.
Always compare this here or 2, 3 into 1.
Yeah, same. Yeah, whatever. 2 bits. With a little bit more of extra, this thing you can handle that.
RP, I had a question.
Yeah, go ahead, Anamay.
Yeah, so you said that we will use these alpha j's as roots of unity. Doesn't it blow up the field size by much?
The
I mean, we
point is
need k plus one.
them as and when you need it. So it's not like you're going to store these roots of unities, like anywhere in local memory, etc. You just store your current value of j and the current value of our I and j. And let's just say you just keep omega written somewhere on the global tape. So on the jth iteration, if you want to compute omega par j, you just do the computation at that point.
Yeah. But so if I need the k plus one as root of unity, does the field have to be large enough to support that, or is field of size k?
I mean,
Okay.
the field will always have a root of unity of basically order -1 because the field will always be, there is a definition of the field.
Okay.
And since I am okay with like literally enumerating all the field elements and trying out and figuring out which is the root of unity also, because all of this I do it once. The field is never changing through the algorithm.
I see. Okay.
So you fix one, you write that down maybe in your global memory somewhere, and then you just, as and when you need it, you compute the alpha, whatever, the omega to the j or something. If alpha j is omega to the j, then that's what you do.
How many such roots do we need?
We just need one. I mean, like every.
No, but even if you take all their powers together, you can become k plus one.
Yeah.
Oh, actually, you can afford to just write down all the alphas once and for all.
Once and for all in the beginning next to you.
Sure. Yeah, we can do that. I mean, like we can actually list down all the, because it's not like you're going to keep on rewriting that again.
You list down all the alpha ones, all the gamma ones.
Yeah, you could actually afford to do that.
Order k log k.
Yeah. So that's in the global memory. It's not like that's going to be rewritten in the recursive calls. Okay, so that's it. So yeah, Taylor. Okay, great. So I can sort of stop here, but I have about 25-ish minutes. Yeah, good.
Is there a suppose you have randomness available? Could you have done better?
So if you have randomness available to you, can you do better?
Probably that's more available.
Yeah, like for example, like just to zoom out, it's like saying, is TEP in RL, for instance? Is your okay? A good point.
It's not obvious.
No, like we don't know if TEP. I mean, like.
Oh, it was supposed to separate P and L.
Yeah.
But we don't know P and L.
Yeah. So okay, is there an easy randomized algorithm for TEP? Actually, I don't see how to use randomness in this situation at all. Yeah.
If the field size was k by log t, you get TP.
Yeah. So okay, just hold on to that thought. I mean, that's what is coming next. So Goldrake's exposition, like what I want to say is like, okay, this is the best space complexity that we know of for the TEP where both H and K are log n. Okay, but you can imagine slightly different situations where you let H and, I mean, in the sense that you could ask, is this expression optimal? Okay, like this looks like H log K plus K log K. And is that really optimal or something? And one of the things that Goldrake does in his exposition is that he notices that this log K doesn't need to get multiplied with K. There is an H log K that seems to be sort of inevitable because of the recursion depth that you have. Okay, so there were log K local memory that you had, and there's a recursion depth of H. So H log K seems like something at least this technique seems to give. But the question is, this extra K log K came from the fact that we started off with 3 registers which were K blocks, and each of those registers we said it holds a field element, and the field element is log K bits. That's where the K log K came from. Now the question is, can you get around it? And once you see that basically what Cook and Mertz were doing was some form of interpolation, there are other versions of interpolation that you could apply that shave off this extra. I mean, it makes the dependence on K slightly better. Okay, so let me tell you briefly how it works. So what Goldrake suggests in his exposition is like saying that previously we were taking the field to be of size about K. And now what Goldrake wants to do is like work with a field that is a little smaller than that. So you set up your field in such a way that you can somehow identify a bit string of length k with something that looks like q elements of the field, where the field itself is of size q. So you're basically identifying 2 par k with something like q par q. Okay, so this is the first thing that you do. So this automatically notice that this is already telling you that you can work with q that looks like k by log k. Okay. And so this is what the value of q is going to be. And now, rather than thinking of the registers as holding 0, 1 to the k, I'm now going to think of the registers as holding f to the mod f. Because 2 par k is basically the same size as q par q, so I can interpret it this way. Now, if you work with all the calculations, it will turn out that you can still show that there is a low degree polynomial that extends whatever you started off with, except that this polynomial will no longer be multilinear. Okay, but we didn't really use multilinearity here. We just said that at the end of the day, I want it to be a low degree polynomial so that I can do interpolation. And if you work through whatever was happening, it turns out you can do a version of multivariate interpolation. It will no longer be multilinear in the xi variables or something. And now, fortunately, the extra k log k came from the fact that we took this 0, 1 to the k and we thought of every bit as now a field element, which incurred this additional blow up of a factor of log k. Now that goes away. And the rest of the algorithm is basically the same. Okay, so what you end up with is like there is 3k plus h, which is your global space, plus there is going to be an whatever h log q, which is the same thing as h log k. That's the space that you have to accumulate as a result of those recursive calls. And this gives you the slightly better dependence, or slightly better dependence for the tree evaluation problem that you have. Basically, it's the same thing. It's the same thing. If there is a polynomial, if you know the polynomial's value on sufficiently many points, you can figure out the polynomial entirely. So you could take a grid of appropriate size and just work with that. I mean, like, so just, yeah, same, probably many ways of doing it. This is probably what I have in mind. Okay, so if you, I mean, Goldreich's exposition is actually very short. I would encourage people to read it. And he actually in fact, I think the section where he does this, I think the title of the section is Tedious Details. And he just goes through it entirely. But this is the overall idea of how you shave off us. I mean, you make the k log k into a k.
And the Goldreich's expression is complete.
It's complete. Like
you don't need to read Cook and Mertz to.
No, you don't need to read Cook and Mertz. Maybe the one thing that you have to take for granted is the fact that those roots of unities and so on, those are things you can compute. But it is, I mean, that part is like, so yeah. Everything else is just.
It's a short expression.
Yeah. And no comments. Okay. Okay. And okay, now in the remaining, I mean, I won't actually take 20 minutes or something. I'll stop perhaps earlier, but I'll just tell you a little bit. You could sort of think of the tree evaluation question where you are working with a tree, but the arity is not like 2, but it's like the fan end is like D or something. I mean, because this will be important for what we do on Friday. Okay, so suppose you work with fan end D instead of fan end.
So we saw last time that we can take an arithmetic formula and evaluate that very space efficiently because it's part of the small matrix.
Yes.
The difference between that and this setting is that every internal node doesn't just contain a simple sum or a product gate or an arithmetic.
Right, it's some arbitrary function. Yeah.
Is there a way of somehow thinking about this algorithm as I don't know, taking this formula, actually implicitly converting it to an arithmetic formula and then running whatever was being run?
Good point.
Because intuitively somehow the same.
Yes. I mean, in the sense that initially it felt like the f had no structure. Right. So you instead replaced it by a low degree polynomial which actually has structure.
Right. So I think there's a natural way of.
Good point. The one catch here is that, we are doing things catalytically, but here it is important how much auxiliary space you have access to. previously I was happily assuming that I have polynomially large auxiliary space. But here, in some sense, my auxiliary space is just this global this thing. So one has to be a little bit more careful.
But in the in Benor and Cleve's final statement, there's not much in terms of. If we forget about how that statement is proven, what we're saying is, if you have a formula here, I can write it as a product of 3 cross 3 matrices with entries from whatever the underlying field.
Right. Your name will do a lot. You reduce this to
Yeah.
this reduction from one input to get another input and then
And
over control.
basically just do basically just multiply matrices one and to the other. It's not a very space intensive.
Yeah, I hadn't thought of this at all.
Intuitively, it seems like the same sort of techniques are somehow at play.
Yeah, I haven't thought about it.
Benor and Cleve didn't have this G0 going to summation gamma I G alpha I. They didn't have that.
No, but I mean, you can think of this as these are things that you have in your instruction set. So you could make use of those. Like Benor and Cleve also, we were basically saying that, I mean, like when we did catalytic space last week, we were only saying that your instructions look like Ri getting replaced by Ri plus Rj, Rk or something. But now we said that no, we will add the scaling register thing also. You will replace Ri with alpha Ri. I mean, yeah, but I don't have a good answer to Kamran's question. But okay, great. So, so when it comes to, let's say, tree evaluation problem with Fallon D, you could basically run essentially the same idea again. And what you will end up with is some space that looks like some space dependency that looks like this. Okay, so it's going to be k times d plus h times log kd. So think of k times d as saying that, in order to compute a node, I need to know the value of my d minus 1 other things. So that's the k times d. And but it's just that, it's not like this is going to get multiplied for every recursion depth. The recursion depth part somehow comes additively. So hopefully the expression sort of at least makes sense. And if you go through the algorithm carefully, set up similar, I mean, like you set up d plus 1 registers and think of programs. First one will operate on register 1, then register 2, then register 3. And then on the dth register, you want the function to be computed. Basically, the same proof will work. Because this is something that we will need for when we do Ryan's. So this is basically all I wanted to say. I will end with just the introduction of Cook and Mertz. I mean, like this is if you look at Cook and Mertz's paper, this is what the introduction reads. In complexity theory, many fundamental questions about time and space remain open, including the relationship to one another. We know that time t is sandwiched between space log t and space t by log t. Both containments are widely considered to be strict, but we have made little progress in proving this fact for any t. And in the next lecture, what we plan to do is show how we can make more than a little progress to basically show that, time t will actually be in space something that looks like square root t, in fact. And okay, and it's one of these facepalm type moments where you will see the proof and then realize that, oh, basically this was just a tree evaluation problem sitting inside. And you just needed to notice that there was a tree evaluation problem sitting inside. And then there's a small set of details that you need to handle. And so I can completely sympathize with, I think Ian sort of being very disappointed that he missed.
But you won't.
This was I checked the introduction of the paper. Sentence 2 of the introduction.
They didn't even know of Ryan's result.
Sorry, which one?
You didn't know of Ryan's result because you and I, we were on the stop.
Okay, there's no comments. But
we did not know of Ryan's result for a few weeks.
Okay. Yeah.
Before, a few weeks ago. Yeah.
Yeah. So okay. So now we have everything we need. In the next class, basically, we'll do Ryan's.
Is there a sort of soft lesson for people writing introduction?
Yeah, read instructions of papers and see what is.
No, but you need. But okay, we'll see this in the next lecture. It's not just Cook and Mertz. It's this other one. You need HPV, no?
Yeah. Yes, we will.
You are going to do HDD in detail? Or?
I won't do it. I mean, the structure is the same.
Okay.
I mean, on a high level, what is okay? So the paper number 18, reference 18 is this paper of Hopcroft, Paul, and Valiant that showed how you can do simulation of time t in space t by log t. Yeah. Okay. And so the way it works is you basically say that you want to simulate a Turing machine. So this Turing machine is going to be at a particular. I want to figure out what is this Turing machine going to do at a particular time. Okay. So for this, I need to figure out the heads are currently pointing at some few places. Let's say if it is a 3-tape Turing machine, there are 3 heads that are sitting around. So to figure out what I need to do, I need to have access to what is the head currently reading at those 3 places. But intuitively, if you know what the heads are reading and what your current state is, etc., you know what to do now. So you can already see this is like a tree evaluation thing, right? If someone told you what you were doing at those 3 places, then figuring out what you need to do now is a function you can write down right away. So basically, just imagine if someone gave you the contents of what the tapes were reading. I need to simulate the Turing machine at, let's say, time step I. So at time step I, tape 1 head was somewhere, tape 2's head was somewhere else, tape 3's head was somewhere else, and maybe the state was something. But basically, if you told me each of these values, like what is the tape currently reading, what is the current state, etc., I know what my Turing machine is doing at this step. So you can think of this as saying that there is a node which is telling you, given those values, I'll tell you what value you're going to take. And so it somehow feels like a tree evaluation problem already. I mean, you just need to, the extra technicality here is like, I don't know where my head is going to be, etc. Those are technicalities we need to deal with. But we can see that, there is a tree evaluation of fan and 3 or something, depending on how many tapes you have. That will show up. And that's what we will see in the next lecture. We will just set up the thing and see that basically it's a tree evaluation sitting inside, and the Cook and Mertz algorithm will tell us how to do simulation of time t in basically space square root t. Okay, so there's no point taking more time. I'll just take questions if there are any.
Ramprasad?
Yeah. Oh.
Yeah, so just a quick question. In Cook and Mertz paper, is it really necessary to use roots of unity or any distinct set of points?
I think you don't need to, because inversion can always be done in, I think, NC2 or something like that. I think you might get a slightly weaker bound because you're only dealing with, like, let's say, K cross K matrices that you need to invert. And K is like log n already. So you could, in principle, I think, work with everything. It's just that when you write it in terms of roots of unities, the interpolation expression is very clean.
You could have just written on alpha 1 to alpha.
Yeah, so
gamma 1 to gamma 2.
That's right, but you still need to compute the gamma 1 through gamma d once. But that computation is like a one-time cost which you can actually afford to. I haven't worked that out, but I suspect that.
Okay.
Sorry?
It will be a log k squared size.
Why is it a log k sized?
K cross.
It's a K cross K matrix. Yeah.
But
Yeah, but you can do this in essentially log of that.
these are very nice. If you take the roots of unity, then
then you can write it explicitly. But I think even if you take arbitrary things, I mean, you can essentially do determinant in polylog space, right? So you just do it for that.
It is the inverse of a ladder mod matrix, not an arbitrary.
Yeah, true. All that is true. Yeah. So I don't think it is absolutely crucial that you have to take roots of unities or something. It's just nicer to work with roots of unity.
Okay. Yeah. Thanks.
There was some other question.
Changing for every.
No. All I care about is I want to do an interpolation for whatever polynomials are going to show up. In order to do the interpolation, I just need more than degree many field elements that I evaluate the polynomial on. So you choose your alpha 1 through alpha 2k plus 1 to be distinct non-zero field elements, write them down in, let's say, your global memory. Now, depending on which j you are, or whatever the loop index, you will have to scale by the corresponding alpha j.
The interpolation every time is being done for a polynomial of degree at most 2k plus 1.
Irrespective of which node you are working with. It is always a polynomial of degree at most 2k.
Alpha and gamma once and for all, write it down. For every interpolation, just use these values. It's an interpolation for a univariate or something.
But VU0 and VU1 are changing.
But doesn't matter. I mean, like, notice that this statement, the fact that G0 can be written as this is true for every polynomial G of degree at most 2k. I don't need to know what G is. Like, it doesn't matter how complicated this polynomial is. This expression is always true.
Any D plus 1 value.
It's like, if you know a line, I mean, it will basically tell you that the value of the line at 1 and 2 will tell you how to compute the value of the line at 3. This is independent of which line you took. There is a fixed linear combination that they will always satisfy. And it's like G is some unknown polynomial. I don't care what it is. At the end of the day, I just want the value of G of 0. And this tells me how to compute.
I have a question.
Yeah.
So probably you covered it in the previous section, but why can't we access tau? Why don't we know the value of tau?
I mean, in the sense we do, but the thing is,
We have to store it in.
I mean, either it is the case that you store it and you later restore it, which means that in order to store it, you will use up extra space. So I want to be space efficient, but my recursive call needs a little bit more space. It's like there was space that was used up by my local, whatever, my local thing or something. And now what we are saying is, okay, fine, you can use that space if you want, but after you finish your computation, whatever is stored there must get restored there. So if you're able to build a program that does this, then you can do it. So this is basically what happens in catalytic space in general. But just that in general catalytic log space, you have logarithmic amount of work tape that you are free to use however you want. There is no restoration that is required, etc. But you have polynomially large auxiliary tape, which starts off at some value you have no control over. And the expectation is that at the end of it, you are supposed to come back to that value. Yeah. So this is sort of that, except that the amount of auxiliary space you have is not polynomially large. It's also quite small. And in that sense, yeah. Okay, great. So that's all I wanted to say. And if there are no more questions, we'll basically meet next week. I mean, sorry, on Friday, day after tomorrow, and see Ryan Williams's result. FU is changing, the tau values could potentially be changing. All that is fine, but it is some polynomial of degree 2k. That's all we need. Once you promise to me that it's some polynomial of degree 2k, my set of alpha i's and gamma i's will always work. That is what is basically being used. Yeah. Any other questions? It's a really cool paper. But, yeah. Okay, great. Then we'll stop here and we will meet day after tomorrow and see Ryan's proof.